In this video, I'm going to talk about Newton's third law of motion. In my earlier videos, I mentioned that force is a quantitative description of interaction between two objects. We even called that there is an agent and an object that interact with each other with a force. So a force that is acting on an object is always the result of the object's interaction with another object. So forces always come in pairs. When you kick a football, the force your foot exerts on the ball launches it into the trajectory, but you also feel the force the ball exerts on your foot. Experiments show that whenever two objects interact, the two forces they exert on each other are equal in magnitude and opposite in direction. This fact is called Newton's third law. To visualize, let's suppose that a man is kicking a ball, and the foot that applies a force on the ball is actually going to this direction, and we name it force of foot on the ball. And there is the opposite force that the ball is exerting on the foot, that is known as force of the ball on the foot. The direction of the forces in this example correspond to repulsive interaction, tending to push the objects apart. However, interactions can also be attractive, such as the gravitational attraction of two masses or the electrical attraction of two particles with opposite changes. Officially, Newton's third law can be written as, if you have two objects, let's say object A and object B, the formal statement for Newton's third law is that force by A on B equals, with the same magnitude and opposite direction, force on B by A, by B on A. Which pretty much means for every action, there is always opposite and equal reaction, or the mutual actions of two objects upon each other are always equal and directed to the contrary parts. This is this statement is translated from Newton's work of Principia from Latin. So Newton's statement means that when A applies a force to B, A itself experiences a force that is equal in magnitude, but in the opposite direction of the force experienced by B. This law applies to only the force between two separate objects. The two forces in this equation format are sometimes referred to as an action-reaction pair. Action-reaction pair. The two forces in an action-reaction pair never act on the same object. That is very, very important to understand, because it might be very contradictory to Newton's second law. If there are always equal and opposite forces, how can there be a non-zero net force? That's why it is important to remember about the force pair of the third law is the action-reaction force do not act on the same object. We can say they switch being an agent and an object. The second law is concerned with the force or forces acting on a particular object or a system. The opposing forces of the third law act on a different object. Hence, these forces cannot cancel each other, nor have a vector sum of zero when the second law is applied to the individual objects. To understand this better, let's consider a situation where a block is sitting on a table and the block has a mass m. And let's see what are the forces on this block, and the mass is m. The obvious force that acts on a block sitting on this table is the Earth's gravitational attraction, which is exerted by the weight. So we put the weight going down like this, and we already know that weight equals mg. Sometimes we just will drop the w and we'll write mg. But there has to be another force acting on the block for the block not to accelerate. The table must exert an upward force of which the magnitude is equal to the block's weight. So we have to have the force, the table exerting an upward force on the block. We call it normal force, so that it will cancel out the weight. If it didn't, then the block would start accelerating. So what we are requesting that sum of the forces should equal to zero. Otherwise, it will accelerate. Because Newton's second law says sum of the forces should equal mass times acceleration. But because the block is at rest on the table, acceleration is zero, so we get sum of the forces equals to the zero. To convert from the vector quantity to the component quantity, we can write sum of the forces by x equals zero, sum of the forces by y equals zero. But then we don't have an x component, we don't care about this part. So then I can write sum of the forces by y axis, where my positive y going up, positive x going to the right, equals zero. So I know that normal force is going to the upward, so it's positive force. Weight is going downwards, it's negative, should equal to zero. From here, we can say normal force equals weight of the object, or equals mg. In reaction to N, the normal force, the block exerts a downward force on a table that is equal by magnitude to N and has opposite direction. As you can see, this is block exerting a force on the table. So the weight and the negative N has two different origin. Weight is the action at the distance gravitation of the gravitational force, and negative N is a contact force between the two surfaces. I'd like to expand a little bit on the normal force here. The normal force in this situation, we found that it equals the mg to its weight. But the normal force is not always equal and opposite to an object's weight. It is very important to understand and realize. The normal force is a reaction force. It reacts to the situation. Here's another example situation where the normal force might be different. let's consider three different situations. This is the first one, second one. We'll discuss by order. Let's suppose that there is an applied force on our block with the mass m at a downward angle. Let's say here's an applied force, some kind of, let's call it F applied. Okay, and in this situation, let's draw our forces. The weight will be still the same. Okay, we'll call it mg. And let's say we don't know what's the normal force. I'm just gonna arbitrarily draw like a force like this, normal force, hoping that it's greater than mg. I don't know, let's check. Okay, so for this one, let's do a free body diagram first, which means we learned how to make the block as a particle and put all the forces down. So this is the block. Now we have the weight going downwards. This is also known as a free body diagram. So that's the weight. And then, as you can see, applied force. Remember, we have to put the tail of the force on the object. So the applied force is going to go this direction. F applied. And then finally, we have the normal force that is going upwards. Okay, so to find what is the normal force, we need to apply, the block is not moving, right? So there is no acceleration. If we apply Newton's second law for this case, we would say sum of the forces equals mass times acceleration, and acceleration is 0, so it equals to 0. And then to get to components, I can substitute sum of the forces by x equals 0 and sum of the forces by y equals 0, this set of equations instead of my vector 1. So that's why we have to first of all choose our x and y axis, and it's very useful to just put the object at the center of the origin. Here's an x, here's an y. Okay, so now to draw x and y components for applied force, I'm gonna bring a perpendicular line to x-axis and to y-axis, and then projection of F applied on the x-axis would be F applied x, and the projection on the y-axis will be F applied y. Okay, now let's not talk about the x-axis because normal force doesn't have. Or we can just write, let's just write it. For some of the forces, we have only applied force x component that equals to 0. And then for the y-axis, since we have resolved the applied force into components, we don't care about this anymore, okay? So for the y component, we have the normal force to be positive, and then we have the mg that is directed towards the negative direction, minus mg, and F applied y equals 0. From here, I can find the normal force equals mg plus F applied y, which means normal force is actually greater than mg in this situation, not equal. It's very important to understand. Now, on the next scenario, let's say we have a force that is going to the right direction at a positive angle. So here's the angle theta, for example. Okay, and then the force that acts on it, it's the mg. And let's say we don't know what's the normal force magnitude is. I'm just putting an arbitrary. Okay, so we'll do again the model of particle model or free body diagram, the way you want to call it. And then so we have the mg going downwards. In fact, you can stop the video here and do it yourself and check it later. So mg going downwards, normal force going upwards, and then we have the applied force that is at the theta angle to the horizontal, F applied. And let's put our x and y axis. So this is positive y, this is negative y, and here's it's very important to mention what's your positive and negative, because sometimes it's convenient to switch the positive and negative. So I'm going to have positive x, negative x here, and then we do the same thing, resolve the F applied into components. So here we have F applied x component, and we have F applied y component. I want you to know that the F applied starts from this particle. It's just like I don't want to overlap the two drawings. I just want to visually be seen. Now, applying Newton's second law, I can say again, I can use the same reasoning as in the beginning, and let me immediately write some of the forces by y equals, remember we don't need this anymore, so equals F applied by y, which is positive, plus normal force equals mg. So from here we can find the normal force. Actually, I was supposed to write minus mg equals 0, and from here I can find the normal force equals mg minus force applied y, which is less than the mg. So here n is less than the weight of the object. Another situation. And finally, we have a situation where we have our block sitting on an incline that is tilted at angle theta. So in these cases, it's very convenient to use tilted axis. There would be a video on tilted axis. Look for it. Now let's put all the forces down here. First one, we go the mg downwards, and then we have the normal force that the surface is pushing up. Okay, and let's say there is no applied force. Okay, so if I draw my x and y axis first, and as I said, the tilted axis, it's convenient to use the x-axis parallel to the tilt. So I'm going to have this one to be my positive x, negative x, and then perpendicular line will make it positive y, negative y. Okay, and so here at the origin I put my object. Now if you see, mg is always downwards, the tail of mg, here we go, that's the weight, and then the normal force is always perpendicular to the surface. Okay, So here's a normal. Now, what we need to do, resolve the mg. Oh, by the way, geometrical. There is a theorem in geometry that that will prove that this angle that mg is making with the y is the same as theta, the tilt of the surface. So then when we resolve the mg into components, x and y components, so this would be my mg y component, and right here would be mg x component. So starting with the Newton's laws, Newton's second law here. Oops, I don't know what was that, but here you go. Okay, I can write sum of the forces by x equals m acceleration by x, which is 0 because our box is sitting there. I mean, you might consider that there is a friction, but we're gonna ignore the friction at this moment. And then sum of the forces by y equals may equals 0. So this is the Newton's second law in a component form. Now, for sum of the forces by x, I can write mgx equals 0. Sum of the forces by y equals normal force minus mgy equals 0. One thing that I forgot to take into account, that my mgx is going to the negative x direction, so I have to write negative mgx. Now we also can find the mgx component equals mg cosine theta. Always remember, mgy is the adjacent to the angle theta, so we use cosine. And mgy, did I make a mistake? Yes, I did. It's a mgy and I wrote mgx. And mgx is the sine because mgx is the same as in here, so it's opposite to angle theta. So mg sine theta. Now we can write from this last equation, n equals mgy or n equals mg cosine theta. As you can see, every time you use the normal force, it is very specific to the situation. Thanks for watching. Stay tuned for more to come.